Good morning, students. Myself, A. Srinivas, Assistant Professor, Department of ECE, Kagatya Institute of Technology and Science, Warangal. Welcome to video lecture on microwave and optical fiber communications. The subject code is U18EC702C. Topic: high frequency limitations of conventional tubes at microwave frequency. Drawbacks of conventional tubes at microwave frequency. At microwave frequencies, the size of the electronic devices required for generation of microwave energy becomes smaller and smaller. This results in lesser power handling capability and increased noise levels. The conventional devices like diodes and transistors cannot be used for frequencies above 100 MHz. The following are the high frequency limitations of conventional tubes at microwave frequency. 1. Inter-electrode capacitance effect. 2. Lead inductance effect. 3. Transit time effect. 4. Gain bandwidth limitation. 5. Effect due to RF losses. 6. Radiation losses. The first one is inter-electrode capacitance effect. Now here, from this figure, you can observe this is a triode. This is a triode at low frequency. This is a triode at low frequency. You can observe it is a three-terminal device. It is a three-terminal device. Now here you can observe the equivalent circuit of the same triode at microwave frequency. At microwave frequency, here you can observe some inductance and capacitance are appearing inside the equivalent circuit. Now here our discussion is about inter-electrode capacitance effect. The capacitance value is given by C is equal to epsilon naught A by D. Let it be equation number 2. Some X is equal to 1 by 2 pi F. It's reactance. Regarding inter-electrode capacitance effect, as frequency increases, the reactance decreases and the net output voltage decreases due to shunting effect. The effect of inter-electrode capacitance can be minimized by reducing the inter-electrode capacitance values CZK, CPK and CZZ. These can be minimized by decreasing the area of the electrodes or by increasing the distance between the electrodes. That is here IEC. Inter-electrode capacitance effect can be minimized by reducing capacitor value, and this can be minimized by reducing the area of the plates or increasing the distance between the plates. The second one is lead inductance effect. Once again, the same concept. This is the equivalent circuit of the triode at low frequency, and this is the equivalent circuit of the same triode at microwave frequency. Here the value of inductance is given by L is equal to small l, length of the lead divided by mu naught mu r A, area of the lead. XL is equal to 2 pi F into L. Let it be equation number 3 and 4. Here you can observe the reactance, how the reactance associated with frequency. As frequency increases, the reactance XL increases and the output voltage appearing at the active electrodes are less than the voltages appearing at the base pins. Means here the voltage appearing at this particular pin, let it be V1, and the voltage appearing at this particular original base pin, let it be V2, due to lead inductance effect or due to inter-electrode capacitance effect, the value of V1 is less than V2. There is some drop inside this particular component. And here The effect of lead inductance can be minimized by using larger sized short leads. This, however, reduces the power handling capability of the device. You can observe the interlink relation here. Transit time effect. Transit time means here this is the position of cathode and this is the position of anode. This is the position of anode. Here we are applying some DC voltage. The electrons are the generated electrons are moving from cathode to anode with some velocity v naught. The distance between the cathode and anode is small d. Okay, the transit time is uh, the distance, the time taken by the electron to travel from cathode to anode, and it is given by transit time tau equal to d by v naught. D is the distance between anode and cathode. V naught is electron velocity. Static energy EV. V is the supply voltage. And kinetic energy is 1 by 2 mv naught square. mv naught square. And here under equilibrium condition, the static energy is equal to kinetic energy. And from this, we'll get the value of transit time as tau is equal to d by root of 2 ev by m. E is electron charge, V is the DC voltage, M is electron mass. Transit time effect continue. To minimize transit time effect, the separation between the electrodes D can be decreased. This could increase inter-electrode capacitance. Means there should be a trade-off between inter-electrode capacitance and transit time. Gain bandwidth limitation. In conventional tubes, the product of conventional tubes means diodes or transistors. Diodes or transistors are vacuum tubes. In conventional tubes, the product of gain and bandwidth is constant. That is, higher gain can be achieved at the cost of bandwidth. Gain into bandwidth is always a constant. In microwave tubes, the restriction can be overcome by the use of reentrant cavities and slow wave structure. That is, larger gain over a wide bandwidth can be achieved in microwave circuitry. Fifth one, effect due to RF losses. In that, skin effect losses. Here from this figure you can observe the skin depth delta, how it is associated with the effective area of a material, and this particular formula we already studied in EMTL subject electromagnetic waves and transmission lines. Some, it will be equation number 4. Just assume it is equation number 4, 5. Just assume 5. Here uh, the skin depth is inversely proportional to frequency, and here from this particular figure you can observe the skin depth is proportional to effective area. uh, from these two relations we can draw effective area is proportional to 1 by root f, and here this is the definition of resistance. R is equal to rho L by effective area, and by substituting these two we get R is equal to rho L by 1 by root F, means here R equal to rho L root F. R is associated with losses, means as frequency increases, losses will also increase. Hence, losses will increase at higher frequency. These can be reduced by increasing the size of the conductors. The next is effect due to RF losses, B dielectric losses. The dielectric losses, the loss in any of the material is given by the power loss is equal to pi f v naught square. Here v naught is the supply voltage, epsilon r dielectric constant, relative permittivity of the medium, and tan alpha. Tan alpha, here alpha is the loss tangent of the dielectric medium. As frequency increases, the power loss increases. The remedy for this is to eliminate the tube base and to reduce the surface area of the glass. Radiation losses. Radiation losses increases with increase in frequency. The remedy for this is to use proper shielding of the tube and its circuit. Here you can see few tubes which are available at UHF frequency. These are acorn tube, doorknob tube, um, pencil triode, lighthouse tube, closed space triode, resonatron, like that. Here, the conventional devices can be used up to some 100 megahertz, up to few megahertz. And here, the UHF tubes can be used at UHF frequency only. UHF frequency only. So here, these tubes are having some drawbacks. To overcome the drawbacks of these tubes, uh, it is better to use microwave tubes. To overcome the drawbacks of conventional tubes and UHF tubes at microwave frequency, it is better to use microwave tubes. Questions? You just make a glance. Dear students, you are supposed to answer during your regular classwork time. Thank you. We will meet with the next lecture.